Welcome to all. In this lecture session, we will start the fourth unit. In this fourth unit, we are having two types of power electronic converters. One is AC voltage controllers and another one is cycloconverters. Both these power electronic converters are having input component as AC as well as output component is also AC. That means these are AC to AC converters. In this lecture session, we will see the principle of operation of AC voltage controller and its analysis with resistive load. So this AC voltage controller is also known as AC voltage regulator. So we'll start the principle of operation. So here we can find the basic block diagram of the AC voltage controller. So basically AC voltage controller is a solid state converter which converts fixed AC voltage into variable AC voltage at constant frequency. So this is something similar to the transformer operation. So in the transformer, one level of input voltage is converted into another level of output voltage at constant frequency based upon its turns ratio. If you want to variable voltage in the transformer, we require tap changings. So by manually changing these tappings, you can have the variable voltage in the transformer. But in the case of AC voltage controller, simply by changing the firing angle given to the power semiconductor devices in the AC voltage controller, we can have the variable voltage. So the minimum voltage we can obtain at the output of AC voltage controller is 0 volts, and the maximum voltage which is equal to source voltage. So this minimum voltage can be obtained at 180-degree firing angle, and this Vs can be obtained at 0 firing angle. By changing the firing angle from 0 to 180 degrees, we can control the voltage from Vs to 0. Alright, so the voltage controller in the AC voltage controller is much simpler compared to the transformer, and the size of the AC voltage controller is much smaller compared to the bulky transformer. So because of these advantages, AC voltage controllers are popularly used in lighting control, fan speed control, and industrial heating. So if you connect a light load at the output of AC voltage controller, it gives variable voltage. So if you give this variable voltage to the light, the intensity of the light will change based upon the voltage. If you are having more voltage, more intensity of the light. If you are having the low voltage, low intensity of the light. So if you want to change the intensity of the light, we can use the AC voltage controller. And the second one is fan speed control. So usually in the household applications, a single phase induction motor used for the fans. So by changing the voltage level for this induction motor, there will be a change in your speed. So by using a single phase AC voltage controller, the input voltage to the induction motor will be controlled so that the speed also will be controlled. In industries, a three-phase induction motor based fans are used for cooling purpose. So again, we can use a three-phase AC voltage controller there so that the voltage given to the three-phase induction motor can be controlled, which controls the speed of the induction motor based upon its cooling requirement. So other application is industrial heating. So by giving the different voltage levels to the heating circuit, we can have the different temperatures. So simply to have the required temperature, you need to give required voltage to the heating circuit. So these are the various applications for AC voltage controllers we are having. So in this introduction, we can summarize that simply by changing the firing angle of the power semiconductor devices in the AC voltage controller, we can control the voltage from Vs to 0. So this concludes the introduction part. So before going to the circuit analysis, we need to know the one point. The thing is, when we have studied about rectifiers, we have considered ideal switches. So ideal switch, when the ideal switch is in off condition, that ideal switch is replaced with open circuit. Switch voltage will be Vs, switch current will be 0. Similarly, when the ideal switch is in on condition, that will be replaced with short circuit. V switch will be 0 and I switch will be load current. So these are the assumptions we have made with ideal switch. Now if we are having a practical switch, so first consider the switch is in off condition, so open circuited, there is no issue with that. Switch voltage will be Vs and switch current will be small leakage current. It is not 0 in practical switch. So when the junction is reverse biased, there will be a small leakage current will flow, so that leakage current will flow from anode to cathode or cathode to anode. So when the switch is in on condition, it will be represented with short circuit here, and switch voltage is not 0, it is on state voltage drop. Usually for thyristors it is around 1.5 volts, and switch current will be load current. Alright, so these two are the changes we can observe from ideal switch to the practical switch. Particularly this point we need to highlight during the analysis of AC voltage controllers. So remember, for AC voltage controllers, when the switch is in on state, that is when it is represented with short circuit, the switch voltage is not 0, it is on state voltage drop something around 1.5 volts. So if you know this point only, you can easily analyze this single phase AC voltage controller with RL load. Otherwise, it is difficult to analyze a single phase AC voltage controller with RL load. So please note that when the switch is in on condition, the on state voltage drop is around 1.5 volts. It is not 0. Now, with this point, we can move to the single phase AC voltage controller with resistive load. So the simplest load is resistive load. Here the power circuit for single phase AC voltage controller with R load is shown. Here this is the single phase AC source which is having phase terminal and the neutral terminal, and AC voltage controller is formed in the form of two anti-parallel connected SCRs T1 and T2. If you carefully observe, these two thyristors are connected in anti-parallel, and the load part, it is the resistive load. The source current is IS, thyristor 1 voltage is VT1, thyristor 2 voltage is VT2, output current is I0 and output voltage is V0. So output is nothing but load voltage and load current. So basically this power circuit contains its source, its power electronic converter, its load, and the control circuit is not shown in this figure. However, we are assuming that the control signals are coming from the control circuit to the gate terminals of T1 and T2. Let us assume we are having a AC voltage supply, just take one cycle. So positive half cycle 0 to pi, negative half cycle pi to 2 pi. So this is my source voltage Vs. Alright. So during positive half cycle of the supply, the phase terminal polarity is positive and neutral terminal polarity will be negative. So during positive half cycle of Vs, phase terminal is having positive polarity, neutral terminal is having negative polarity. So this positive polarity is applied at T1 anode, and this positive polarity is applied at T2 cathode, so that T1 will be in forward blocking mode, T2 will be in reverse blocking mode during the positive half cycle of the supply, so that I can give triggering pulse to alpha to T1 during the positive half cycle of the supply. Now at pi, the polarity of the source voltage gets reversed. That means it is the starting point of negative half cycle. So during negative half cycle, phase terminal becomes negative, neutral terminal becomes positive. So negative half cycle. So during negative half cycle of the supply, phase terminal is negative, neutral terminal is positive. So this minus is applied at anode of T1 and cathode of T2, so that T1 will be in reverse blocking mode, T2 will be in forward blocking mode. So I can give triggering pulse to T2 under these conditions. So if you understand these conditions, we can easily analyze the single phase AC voltage controller. So we'll see the current path when T1 is in on condition, when T2 is in on condition. So let us assume now T1 is in on condition, so that T1 can be replaced with short circuit. So the current flow starts from phase terminal to T2, sorry, T1 to resistive load to neutral. So this is the current path when T1 is in conduction. So when T2 is in conduction, the current flow starts from neutral to resistor to T2 to phase terminal. So this is the current path when T2 is in operation. So I can expect a positive half cycle when T1 is in conduction. I can expect a negative half cycle when T2 is in conduction. So to have the complete picture of this analysis, we can divide one cycle of the source voltage into different modes. So if you observe here, we are having a source voltage. So based upon the source voltage, we need to analyze output voltage V0, we need to analyze the output current I0, Thyristor 1 voltage, Thyristor 2 voltage. So these are the various components we need to analyze for one complete cycle. So to make our analysis simpler, we need to divide one complete cycle into different modes. For that, first identify the zero crossings of the source voltage. So zero crossings are at pi, 2 pi and 3 pi, and these are indicated with dark black lines in this figure. Next, indicate the triggering instance. So alpha is the triggering instant for T1, pi plus alpha is the triggering instant for T2, and 2 pi plus alpha is the triggering instant for T1 again. So this alpha may be 0 degrees, this alpha may be 30 degrees, or this alpha may be 90. So based upon your output voltage requirement. So this alpha is the variable thing. So as it is R load, both voltage and current comes to the zero crossing point at the same time. So there is no need of indicating the beta instance here. So now we can divide this operation into different modes. So mode 1 from 0 crossing to triggering instant, that means 0 to alpha. Mode 2, triggering instant to 0 crossing, that means alpha to pi. Mode 3, 0 crossing instant to triggering instant, that is pi to pi plus alpha. Mode 4, triggering instant to 0 crossing, so pi plus alpha to 2 pi. If you observe, we have started at 0, we have only ended up with 2 pi, so that one complete cycle analysis is obtained in these modes of operation. So mode 1, mode 2, so from 0 crossing to triggering, triggering to 0 crossing, again 0 crossing to triggering, again triggering to 0 crossing. So these are the various things we are having. Alright, now we'll see the analysis of mode 1. So in mode 1, positive 0 is the starting point of positive half cycle. So T1 will be in forward blocking mode of state, T2 is in reverse blocking mode, again off state. So both T1 and T2 are in off state, so that output voltage will be 0 volts, output current is 0, and I'll write VT1 here. So VT1 is off state, it will be Vs. VT2 is also off, T2 is also off state, so it is also Vs. But T1 is in forward blocking mode, I'm having positive Vs. T2 is in reverse blocking mode, I'm having negative Vs. So these are the various components for mode 1. If it comes to the mode 2, so alpha is the triggering instant for T1. So T1 goes to on state in this mode, T2 still it is in reverse blocking mode, so that off state V0 is equal to Vs, as the load is connected to the source and the current path is from phase to T1 to load to neutral. So this is the current path. Now VT1, now the T1 is in on state, so that it is not 0, it is on state voltage drop. Now what about VT2? So T2 is in off state, so it should be Vs, right? But it is not Vs because both T1 and T2 are connected in parallel. So when the Thyristor 1 voltage is on state voltage drop, Thyristor 2 voltage is also on state voltage drop, and this will be positive and this will be negative because it is reverse blocking. T2 is in reverse blocking. So this is the analysis of mode. And now it comes to mode 3. At pi, voltage becomes 0, so that reverse voltage is applied to T1. And one more thing, current also becomes 0 at this point. That means Thyristor 1 current drops below the holding current. So T1 goes to off state at pi. So we can consider T1 goes to reverse blocking mode at pi. And T2 goes to forward blocking mode. It is also off state. So both the switches are in off state, V0 0, I0 is also 0. Then VT1 is Vs, VT2 is also Vs. So it is reverse blocking mode, negative, it is forward blocking mode, positive. Alright, now when it comes to mode 4, at pi plus alpha, triggering pulse is given to T2, it goes to on state, and T1 will be in still reverse blocking mode, it should be in off state. So V0 is equal to Vs, and I0 path is from neutral to load, load to T2, T2 to phase. and Thyristor 1 voltage is based upon Thyristor 2 voltage. So Thyristor 2 voltage is on state voltage drop, so that Thyristor 1 voltage is also on state voltage drop, but it is negative here, it is positive here. So we have obtained the information of output voltage, output current, Thyristor 1 voltage and Thyristor 2 voltage for all the 4 modes. So we'll complete the waveforms. So during mode 1 the output voltage is 0, so we can draw the 0 voltage here. And in mode 2, that is alpha to pi, the output voltage is equal to Vs. So this is the starting point of our source voltage, so we can draw the output voltage like this. So if we consider this as Vm, peak amplitude, this is my peak amplitude. Now in mode 3 the output voltage will be 0, and in mode 4 the output voltage is equal to Vs. Alright, next, so 4 modes are completed. Again, this is the first mode, output voltage is 0 and output voltage is equal to Vs. So this is the output voltage waveform for AC voltage controller with R load. When it comes to the current waveform, in mode 1 current is 0, and in mode 2 there is a current flow. As it is R load, the current wave shape is similar to the voltage wave shape, and the peak amplitude is Vm by R. In mode 3 the current is 0, in mode 4 we are having the current flow, but it is in the negative direction. So again, mode 1, mode 2, the same thing will be repeated. Now when it comes to the Thyristor voltage, during mode 1 Thyristor 1 voltage is plus Vs, so this part, and mode 2 on state voltage drop, it is not 0, so this is your Vt. During mode 3 minus Vs, during mode 4 minus Vt. Again mode 1 plus Vs, mode 2 plus Vt. Similarly, there is 2 voltage during mode 1 minus Vs, during mode 2 minus Vt, during mode 3 plus Vs, during mode 4 plus Vt. Again mode 1 minus Vs, mode 2 minus Vt. Remember, here I have deliberately uh, omitted the KVL. In general, Vs is equal to Vt plus V0. So anyway, V0 1.5 volts. If it is 230 volts, it is uh, very less. So that's why I have not considered this KVL application in this waveform analysis. Anyway, that is our convenience. So please note this point, and if you have any doubts on this point, we can discuss it later. Alright, so we have drawn the various waveforms, that is output voltage. Remember, don't confuse between output voltage, output current and Thyristor voltage waveforms whatsoever. Now these are the textbook waveforms I have taken for the better wave shapes. Alright, so same mode 1, mode 2, mode 3, mode 4. So from these waveforms we can compute the various voltage components and current components, output voltage components, Thyristor current components, input power factor, all these things we can obtain from these waveforms. Alright, okay, fine. So the first output voltage component is V0 average. So generally average component is the DC component. So if you see the AC voltage controller output waveform, the positive wave shape area is equal to negative wave shape area in one compute cycle. So the average output voltage is 0. So the DC component is 0. So you need not to calculate average component for AC voltage controllers. So other thing is RMS component. So this is the generalized formula what we are having for RMS component. Here the total period is 2 pi. So 2 pi is the total time period. So this waveform is following half wave symmetry. So I can integrate during positive half cycle. During this positive half cycle I am having the voltage part from alpha to pi. So the limits are alpha to pi. It is following half wave symmetry. So Vm square sin square omega t is the voltage. So half wave symmetry, just I need to multiply this integration with 2 so that I can get the required RMS output voltage. Now RMS output current is this the ratio of RMS voltage to the resistance. Now this is about output components. When it comes to the thyristor currents, so if I want to calculate the IT average, I need to have V0 average by R. You know that T1 conducts for positive half cycle, T2 conducts for negative half cycle. So I need to calculate average component for one half cycle, but the duration is 2 full cycle. So V0 average, so 1 by 2 pi r, so T1 conducts from alpha to pi, so the average component formula Vs, so that Vm sin omega t d omega t. Anyway this R is here, so in this way we can calculate the thyristor average current. Now when it comes to RMS component, so V0 RMS by resistance. However, there is no multiplication factor of 2 because each thyristor conducts for only one half cycle. So ITrms. So if you carefully observe, the difference is root 2 in the denominator. So both are same, more or less same, except here it is for one complete cycle, it is for half cycle. So thyristor average current, thyristor RMS current. Now average power delivered to the load. So we're having RMS component voltage, so that this is the formula we can use for power delivered to the load. Now another thing is input power factor. So real power, nothing but active power. So power factor is the ratio of real power to the apparent power. So real power can be obtained from the same formula, that is of P0, and apparent power, so input RMS voltage into input RMS current. As we know that input current is equal to load current, so IS is equal to I0 RMS. So apparent power is nothing but Vs into I0 RMS. So we know V0 RMS, I0 RMS is equal to V0 RMS by R. So the power factor finally we obtain is the ratio of output RMS component to the input RMS component of voltage. So these are the various things we can see for single phase AC voltage controller. We'll see one more time a recap of single phase AC voltage controller with R load. Simply during positive half cycle, T1 will be in forward blocking mode. I can give triggering pulse to T1 and T2 will be in reverse blocking mode. During negative half cycle of the supply, T1 will be in reverse blocking mode and T2 will be in forward blocking mode. So I can give triggering pulse to T2. So when T1 is in conduction, so if I give triggering pulse to T1, T1 goes to on state obviously. So when T1 is in conduction, the current flow starts from phase to T1, T1 to load to neutral. Similarly, when T2 is in conduction, the current flow starts from neutral to load to T2 to phase. Alright, now so we have divided one complete cycle operation into 4 different modes based upon zero crossing points and triggering signals. So based upon its thyristor states, whether it is in forward blocking, forward conduction, reverse blocking, we have identified the output voltage, output current, thyristor 1 voltage and thyristor 2 voltage, and we have completed the waveforms. Based upon the waveforms, we have calculated the output RMS voltage, Thyristor average current, Thyristor RMS current, and average power delivered to the load, finally input power factor. So this is the analysis of single phase AC voltage controller with RLO. In the next lecture session, we will talk about single phase AC voltage controller with RLO. Thank you.